Hello and welcome to this lecture on turbo codes. Let us start with the outline of today's talk. We would have a quick introduction to turbo codes followed by the encoding process. Then what makes turbo code very interesting is the decoding process, from which it also derives its name. Then we look at a very interesting component of these turbo codes called interleavers, and finally we will look at some examples. So, that is the outline for today's talk. What we have done so far, we can have a quick recap. We were looking at convolutional codes, and this is the logical end to the topic of convolutional codes, where we looked at the trellis representation, the matrix description, and finally, the popular Viterbi decoding algorithm for convolutional codes. We also looked at some of the known good convolutional codes, and now we change gears and go on to study the next version, which is the turbo codes. So, let us have a quick introduction. So, turbo codes are not very old, but not very new either. They were first proposed in 1993 by 3 inventors, and the title of the paper was Near Shannon Limit Error Correction Coding and Decoding. So, as the title suggests that these were supposed to work close to the Shannon's limit, and that is why it generated a lot of curiosity, and they also showed a better rate performance of 10 to the minus 5 at very low EB over N naught of 0.7 dB, and they used only 1/2 rate code, and this was the starting point for turbo codes. So, they perform well in low SNR scenarios, and that is where we see them touching the Shannon's limit. But at the other end of the spectrum, if you look at high SNR scenarios, the traditional codes such as Reed-Solomon codes that we have studied can outperform turbo codes. So, turbo codes are supposed to be used when we are working in low SNR scenarios, which we can't have enough of. We do have cases, and we would like to preserve battery life. So, we can always lower the transmit power and come into the regime where turbo codes become effective. So, you will shortly see that turbo codes behave like block codes to some extent, but they are kind of an in between convolutional codes and block codes, and it is kind of a quasi mix, so to say. They require the whole block to be received before decoding can start to happen. But rather than computing the parity bits from a system of equations, they use shift registers just like convolutional codes. In fact, turbo codes are a combination of 2 or more convolutional codes separated by an interleaver, as we will shortly see. So, they typically use 2 or more convolutional component encoders, which are separated by an interleaver. This is called concatenation. So, we can have a series concatenation or a parallel concatenation. So, this is the basic structure of a turbo encoder. As you can see, this is the input, and this input can go to the first convolutional encoder called encoder 1, and it gives some output. But the same input goes through an interleaver, which is basically a shuffling operation, and is fed to another convolutional encoder. So, both encoder 1 and encoder 2 are convolutional encoder, very hardware friendly, and we have output coming from encoder 2. These three, so it is some kind of a systematic code. You can say that the input has 2 parity symbols coming out from encoder 1 and encoder 2, and this together forms the output of this turbo encoder. But as you can see that these 2 encoders, the convolutional encoders, can be in several configurations. So, what are the obvious configurations? We can have the parallel concatenated convolutional encoder, which we just now see. we have seen that this encoder 1 and encoder 2 are in parallel, but nothing stops them from putting an encoder 1, then an interleaver in series and then an encoder 2. So, you can have a serial concatenated convolutional code. So, SCCC as opposed to PCCC, and you can always have a hybrid, a combination of a serial and parallel, giving us the name hybrid concatenated convolutional encoder or HCCC. But in most of the cases we will be working with PCCC. Okay. And what is an interleaver? It is denoted by pi. It is nothing but a permutation I goes to pi I, which changes an order of the data sequence of n input symbols d1, d2 up to dn. So, it is just a permutation that happens because of the interleaver. Earlier interleavers were used to ensure that block codes can work where we have a run of errors, burst errors that happen. So, interleaver were used to separate out the burst errors into random errors, and then the block codes could work. Here the interleaver is being used for a very different purpose, as we will shortly point out. So, if the input data sequence D is D1, D2 up to Dn, then the permutated data sequence is Dp, where P is the interleaving matrix, and it has a single 1 in each row and column, and all other entries are 0. So, it is a sparse matrix, and it is very simply an interleaving matrix multiplied by this vector gives you an interleaved vector. Obviously, I can have a de-interleaver which undoes the operation of the interleaver, and so we denote it by pi inverse, and it restores back the interleaved sequence back to its original sequence. So, the interleaving de-interleaving matrix is simply the transpose of the interleaving matrix P transpose. So, using algebra we can easily show the process of interleaving and de-interleaving. So, we need to ask what is it that the interleaver is doing. Well, the interleaver, as the name suggests, shuffles the input bits in such a way that the input to the second interleaver, the second encoder, is different from the first one. So, let us see why this will work. This will result in high weight code words. If you remember, the simple convolutional encoder was a linear encoder. So, the weight of the code kind of has a direct correspondence with the D free. So, we are concerned with high weight code words leading to better error correcting capability. Now, you must know that D free corresponds to the minimum free distance, which means that we are looking at the worst case scenario. It does not mean that all sequences have poor weight characteristics. Some of them are good in terms of the distance properties and hence a higher weight, and some of them are poorer. What the turbo code does is it mixes and matches to ensure that you do not end up with a poor weight all the times. Right? So, the interleaver 2, which has the parity which requires an interleaver for the second encoder, will result in a different kind of a output bit stream. So, let us look at it in a slightly more detailed manner. So, as you know, you have a convolutional encoder, we call it encoder 1, and it should give a sequence. Suppose an input sequence was coming in, and this encoder, it could be rate 1 by 2. So, for every bit it gives you 2 bits of input. Okay. Now, if we put the same encoder here, but we label is at encoder 2, and it is again rate 1 by 2. if we had given the same input here, I would get the same output, but we do not want that. So, we put it through an interleaver, and what it does is it gives to this encoder something which is permuted. Now, clearly the output of the second encoder will be different from what was received earlier.
Is this shuffling random?
Okay. Question being asked is the interleaver random? Random interleaver is one type of several possible interleaver, and at the end of today's class we will talk about the different kinds of interleaver, but random interleavers also work very well. So, right now let us say it is just a random interleaver. So, there is no constraint, it randomly permutes this combination. But what has resulted in this one? The output, if this was rate 1 by 2, for every 1 bit that comes in, 2 bits go out. Okay. Similarly, 1 bit comes in, 2 bits go out. So, the output here is a path in the trellis, because this is a convolutional encoder. Now, this path in the trellis will have some weight. Now, clearly this encoder with a different input has another path in the trellis, because the input bit stream decides which path in the trellis you give, and therefore, the output is a different bit stream. Now, if one of the paths corresponds to the D free, or it is a poor weight, the D free is resulting from the one which has low weight, then obviously this being a random interleaver, this output sequence will be different from the first one. So, if this is low or lowest possible weight, this will not be, in fact, this could be very most likely a high weight. So, if we can combine these two, on an average we will come out a winner. So, a low weight path gets combined with a high weight path, and together they balance out, and we do not kind of have a path which has low weight, because effectively the worst case analysis leads to the D free. Okay? But there are many paths which are high weight. So, chances of them combining leading to a path with a good weight is very high, and that is why a random interleaver just works. So, if you look at this a little bit more carefully, you have now an input to an encoder which is suppose rate 1 by 2. So, you will have an output which has 2 bits out, but this goes through an interleaver and goes through another encoder, again rate by 2, again it has 2 bits coming out of here. So, you have 1 bit going in and you have 1, 2, 3, 4 bits, and it is not a surprise, because you have rate 1 by 2 and rate 1 by 2 leading to an effective rate 1 by 4. Now, this is pretty expensive in terms of the extra bits we are padding, because we are resulting in rate 1 by 4. So, it is possible to, so to say, drop 1 bits at a random, which is called puncturing. So, we can possibly drop one of them, and if really this guy is actually a systematic encoder, then this first bit is identical to this one, but not this one, because this comes from an interleaved version. So, you can drop any one of them. So, I can lead this rate 1 by 4 to back to 1 by 2 if I cancel out both of them, or I can take it to 1 by 3 if I just just drop one of them. This is the puncturing process. So, I am introducing errors by myself, but what the strong encoder decoder can do is to recover from this error, self introduced error. Okay. So, we come back to the slides. And we now focus our attention on the decoding part, because we have just now understood that encoding is very easy, it is fairly hardware friendly. So, the encoder determines the capability for error correction, it is a decoder that determines the performance. There is a difference. There is a difference between the capability and actual performance. So, you can have several kinds of decoders, and we will discuss two of them briefly at the end of this lecture. So, there is a decoder which will decide the performance. So, the performance depends on the algorithm used, and turbo decoding is an iterative decoding process. Please note, this is a basic difference between decoding a Viterbi based convolutional code and this turbo codes. Turbo codes require an iterative decoding process. For example, the maximum a posteriori algorithm MAP or the soft output Viterbi algorithm SOVA for decoding. So, soft output algorithms outperform hard decision decoding algorithms, because they have available a better estimate of what the data sent was actually. And soft output yields a gradient of information, as opposed to hard decision decoding, which is like choosing 1 or 0 right in the beginning, leading to the loss of information. So, let us look at the structure of the turbo decoder. All right. So, here if you see, we have the 3 output bits coming into the decoder, and if you look at the various blocks within the decoder, you have a decoder 1, you have a decoder 2, you have an interleaver and also a de-interleaver, and then again there is an interleaver. So, first we have to understand how it works. In a very basic manner, the job of the decoder is to guess what would have been the real thing and mimic the encoding process. So, you have an interleaver itself. So, encoder, interleaver, encoder, and it compares it with the received vector, finds the difference, adjusts the estimate, and then again does the encoding process, compares with the received vector, compares the difference, and then does it several times till it converges or a threshold is met, and then you get the final estimate and declare the result. So, it has to be an iterative guessing process. So, let us talk quickly about the decoding process. A turbo decoder generally uses an MAP algorithm in at least one of its component decoders. What is MAP? It is a maximum a posteriori algorithm. The decoding process begins by receiving the partial information from the channel and passing it to the first decoder, as we saw. The rest of the information, which is the parity bit 2, goes to the second decoder. So, if you recall, what we have done is we have got, if you go back to the drawing board, we have the original bit coming in. So, it is a systematic, and then I discard one of them and I get y k 1, and I discard this one and I get y k 2. So, yes, I had a rate 1 by 2, I threw out 1, I am confident I will be able to recover from this self imposed error. I discarded 1 here, I got back here. So, I have on this side a rate 1 by 3. So, I am going to work with these 3 bits at the decoder. Now, please note, x k, y k 1 will be fed, this is called the partial information, this will be fed to decoder 1, and this really corresponds to encoder 2. So, it will be fed to decoder 2, and we will have a message information passing algorithm, which they will share the information and together try to guess what could have been sent so as to give me xk, yk1 and yk2. That is the strategy. So, we go back to our original slide and we see that the decoding process begins by receiving the partial information xk and yk1 and passing on to the first decoder within the turbo decoder. And the rest of the information parity 2, which is yk2, goes to the second decoder and waits for the rest of the information to catch up. While the second decoder is waiting, the first decoder makes an estimate of the transmitted information, because it knows what the encoder was, encoder 1 was, and it makes an estimate, right, and then interleaves it to match the format for parity 2, because the decoder 2 can work with only an interleaved data. So, it makes an estimate, hoping it is right, does the interleaving and gives it to decoder 2 to generate its output. Now, the decoder 2, the second decoder takes the information both from the first decoder and the channel and re-estimates the information. This second estimation is looped back to the first encoder where the process starts again. So, it is message passing. Therefore, it is clearly an iterative process and we keep doing it till we converge and we know that okay, this is the best bet I had in terms of the received message. So, clearly it needs some time to converge. So, this is what we had sent, this yk goes to yk2 goes to decoder 2, yk1 and xk goes to decoder 1, it gives an estimate. So, it interleaves and passes on to decoder 2, so that it can mimic the encoder 2 and then it together does a deinterleaving and passes the message. So, it goes on and on. So, graphically let us see what is happening. Let us start with the input data, and input data is sent from the channel to the first decoder. We have seen that, which makes an estimate based on the information, and then it transfers the estimates to the first decoder, receives the information from the channel to the second decoder, makes a new estimate based on the information and transfer the estimate to the second decoder. The reason this is exactly what we had discussed, why we have put it in this way is to show an iterative decoding process. Okay. And finally, when we are happy or the convergence happens, we show the output, and this loop must keep on going till we are ready to declare the results. So, why is it called a turbo decoder? Well, if you see the turbo engine, it also has an engine here and an exhaust gas discharge here, and it somehow has a loop like this which works, and therefore, this is called the turbo decoder. This is how the name has come. Why is it called a turbo decoder? It has a, or it is some similarity with a little bit of imagination with this turbo engine. Question now is, we had this very nice Viterbi decoding algorithm for convolution encoder. Here we have two convolution encoders. Why can't we use Viterbi to decode? Well, the problem is that we do not have the luxury of a single trellis anymore. Okay? Why? Because even though the first encoder uses a trellis diagram, the input to the second one is based on a permuted sequence, and therefore, it corresponds to some other trellis. So, the Viterbi algorithm works by systematic elimination of paths in the trellis, but the question is which trellis. Okay? But we do not have this luck for turbo decoder, and therefore, that iterative decoding must work. So, we must appreciate that Viterbi can work if you specify a deterministic trellis, not that a trellis that keeps changing. So, this presence of this interleaver has really complicated this decoding process. So, let us just now spend some time looking at two popular decoding algorithms. So, before the discovery of turbo codes, a lot of work was done in the area of suboptimal decoding strategies for concatenated codes. So, anyway the work was going on. Now, the symbol by symbol maximum a posteriori map algorithm by Bhal, Kokek, Jelinek and Raviv, which is called the BCJR algorithm, was published in 74, but it was there on the library shelves, not much was being done till in 1993 it was reused by Barrow et al. To do turbo decoding. So, what we will discuss today is this BCJR, actually a modified BCJR decoding algorithm for turbo decoding. Okay. So, what is this algorithm? It is just in the next few slides we will put into mathematics the intuitive understanding that we have developed for this turbo decoding, that information passing between encoder 1 and encoder 2. So, first of all, this modified BCJR decoding algorithm is a symbol by symbol decoder. So, the decoder decides that UK is plus 1. So, let us talk about binary. So, plus 1 and minus 1 instead of 1 and 0. So, the decoder decides UK is plus 1 if probability of UK is plus 1 given y, the received vector, greater than probability the UK is equal to minus 1 given the received vector. So, this y boldface is y1, y2, yn is the noisy received word, it could have errors in it. So, what we do is the decision u k hat is the sign of L u k. What is L u k? Is a log a posteriori probability. So, LAPP, we will use this as a way, which is a log likelihood ratio, which we have just now seen the probability of u k is equal to 1 given the noisy stream y versus u k is equal to minus 1 giving the received vector. And if it is now a question of a sign. If the numerator is larger, the sign is positive, the numerator is less, probability is less, the sign is negative. So, we are now only working with the sign. Okay? So, it is a very smart way to convert this log a posteriori probability ratio. So, we are now going to work with this ratio and the signs itself. So, it is pretty decent to do this. So, now we just go into the trellis and for the encoder 1 and encoder 2, and we look at these probabilities. So, we are trying to find out, given this vector y, what is the probability that u k is 1. And similarly, we define these two ratios, and this is in terms of the state of the encoder, right. So, we can do a little bit of maths, and we have these forward and backward gains, which are intermediary terms as alpha tilde and beta tilde with some boundary conditions. So, we can go into the details of this BCJR algorithm basically to define exactly what is the log a posteriori probability in terms of these alphas and betas. So, this is the LAPP ratio. So, based on the sign, then the decoding can happen, all right. That is how you do the estimate. Now, we look at the second decoding algorithm. I will give you a hint as to how it is done. This is called the iterative map decoding. It is different from the BCJR algorithm that we studied before, and here let us look at the methodology. So, you have these 3 inputs that are coming in, and we have now the map decoder 1. Then we have an interleaver giving into map decoder 2. So, you can estimate this capital D 1 and capital D 2, and then we have a D interleaver which passes to decoder 1. We have looked at this block diagram earlier, and then through the interleaver you look at 2 and so on and so forth, and finally, you give the output. So, we are using 2 map decoders operating cooperatively. That is the iterative map decoding algorithm. Again, we will have to use some kind of a likelihood function. So, D 1 and D 2 are 2 decoders, and we have S is the set of 2 raised by m constituent encoder states, y vector is the noisy received word. Then we can use the Bayes rule to write LUK as follows, and the second term representing the a priori information here. So, since probability of UK being 1 and UK equal to -1 typically is equal, then the a priori term is usually 0 for convolutional decoders. Okay. So, what D2 second decoder does is it receives the extrinsic information from D1 and the decoding iteration proceeds with each of the 2 decoders passing the soft information along to the other decoder at each half iteration. So, the idea behind this extrinsic information is that D2 provides soft information to D1 for each UK using only information not available to the decoder 1. Similarly, D1 does for D2. So, they keep passing partial information without declaring the result till the convergence is reached. So, we can define again the intermediary terms. We will not go into details as to how these message passing is actually done, but again we have a ratio depending on the states of the algorithm that we have studied earlier, and it is quite similar to that we have done for the BCJR algorithm. So, you can work this out and you have these expressions for conducting the iterative map decoding, and you have this forward and backward parameters alpha k tilde and beta k tilde. So, for the algorithm, if you go back to the intuitive understanding of how it works, each decoder must have full knowledge of the trellis of the constituent encoders. But since transmitter and receiver are friends, it is not a difficult thing to have. So, you must know the trellis states for the decoding to happen. So, each decoder must have a table containing the input bits and the parity bits for all possible state transition. Okay. So, the state transition diagram must be available, and based on that the alpha and beta are calculated. Also, care should be taken that the last m bits of the n bit information word to be encoded must force encoder 1 to state 0. So, that for the next block we can start afresh. Okay, there should be no ripple effect. The performance of iterative decoding improves if the information that is sent to each decoder from the other decoder is less correlated with the input information data sequence. This is just an observation. So, just let us compare how turbo decoding performs. So, if let us put the axis in place. So, the x axis represents the signal to noise ratio in dB, the y axis represents the bit error rate. So, if you see the greenish curve is no coding is used. So, depending upon the signal to noise ratio, you have a raw error rate which is really unacceptable. And then if you use this Reed-Solomon code, you are somewhere here depending upon what is your signal to noise ratio. So, as you can see that this x axis is SNR. So, Reed-Solomon codes work well at reasonably high SNR. Then if you look at turbo product codes, they are slightly here, but if you look at the recursive systematic convolution turbo code, this is the performance curve for that. It really works at low SNR, and here is the Shannon's limit, by the way. So, relatively speaking, it is much closer to the Shannon's limit, and you can get a remarkable performance. Suppose you are working at 10 raised to minus 5, this is the 10 raised to minus 5, then with respect to uncoded, you can have a humongous 8.5 dB coding gain because of this RCS turbo encoder. Okay. So, let us look at an example how effective it will be in real life. Suppose we are doing deep space communication, where we are having this inverse squared law being followed with respect to the distance. So, this means that the turbo coded signal can be received with 2.65, that is under root 7 times farther away from with respect to the uncoded signals, because it requires 1/7 of the transmit power for the same transmitting distance. So, even if you have large distances, the use of a turbo coder would really require you to use much lesser power, and these are power limited channels. So, it really makes sense. As we saw in this previous diagram of a recursive systematic convolutional RSC turbo encoder, this is the diagram. For a bit array of 10⁻⁻5, we have this minus 8.5 dB. So, this is the coding gain, which is like under root 7, and which gives you the humongous saving in power. So, the battery life tentatively lasts 7 times longer. Okay. Or from the distance, it is almost 2.6 times the distance that can be sent the signal from, so as to get the same performance. So, it is pretty impressive in terms of the performance. Now, we come to this interleaver, which has made our life difficult for decoding purposes, but let us talk briefly about the interleavers. What is the importance, what are the types, how can we design them? So, the superior performance of turbo codes over convolutional codes is achieved only when the length of the interleaver is quite large. Okay. So, since the interleaver must be present, so the interleaver works with a block. So, therefore, this convolutional code lies between block codes and convolutional codes. We work with a block size at a time. So, most random interleavers work well. On the other hand, for some applications, it is preferable to have a deterministic interleaver to reduce the hardware requirements for the interleaving and interleaving process. Okay. For short block length interleavers, the performance of turbo codes with a random interleaver degrades substantially up to a point when its BER performance is worse than the BER performance with convolutional codes, standard convolutional codes with similar computation complexity. So, please note that the short block interleaver, right, that the block length interleaver must be large enough to give you the gain. Otherwise, we will go back to normal and the advantage will wear off, because you are actually puncturing and throwing out some of the bits, right. So, for short block length interleavers, the selection of the type of interleaver does have a significant effect on the performance. So, let us quickly spend some time on the interleaver designs. There are two major criteria for interleaver design. One is the distance spectrum properties, which is the weight distribution of the code. I mean, that is how we started off with. Why are we adding an interleaver? Because for the same input bit stream, if the input bit stream leads to a low weight sequence, then the interleaver should shuffle the bit stream such that the resultant output should be a high weight output. Number 2 criterion is the correlation between the soft output of each decoder corresponding to its parity bits and the information input information sequence should be such that the advantage of decoding is achieved. So, the second criteria of the correlation between soft output of each decoder and the information sequence is called the iterative decoding suitability criteria. So, that is how we design interleavers. So, they have been designed by trial and error, or there are some design rules, and once you fix an interleaver, you are good to go. What about the random interleaver? Well, you do not have any effort in designing it, it is simply a random permutation pi. So, if you define an S random interleaver, is a semi-random interleaver which is constructed as follows. So, it is a compromise between a random and a deterministic. Each randomly selected integer is compared with S, where S could be 1 to a 3 or so and so forth, previously selected random integers. If the difference between the current selection and S previous selections is smaller than S, then the random integer is rejected. So, it is a way of picking random data. This process is repeated until n distinct integers have been selected, and thereby you end up with a S random interleaver. Let us look at an example how it is used in real life. So, the 3GPP, which is the third generation partnership project, proposes the use of turbo code interleaver, and the algorithm is given in this slide. So, the input sequence can be starting from 40 to over 5000. Okay. So, we have to input this large size of a sequence. So, let us summarize the algorithm. So, step 1, you have row wise data input to an R cross C rectangular matrix with 0 padding, right, and k is less than R cross C. So, I have to fit in those many bits into a matrix. Okay. So, R and C represents the rows and columns. Now, intra-row permutation of the rectangular matrix is carried out based on recursively reconstructed base sequence S. Then step 3 is inter-row permutation of the rectangular matrix based on a well defined inter-row permutation pattern T. So, you can specify T, right, and then finally, a column wise data output of the rectangular matrix. If you remember, the most basic form of an interleaver is you feed in the data row wise and read it out column wise, right. But here we put in the data row wise and then do row permutations of two types and then read out the data column wise. Finally, what are the advantages and disadvantages of the turbo codes? Well, let us start with the advantages. Remarkable power efficiency in additive wide Gaussian noise and flat fading channels for moderately low bit error rate. Please note moderately low, because if you put the BR too low, then the convergence does not happen and we do not get good results. And that design trade off suitable for delivery of multimedia data services. What are the disadvantages? Long latency, because it is an iterative algorithm, we have to wait till the entire block is received, iterations happen and decoding is declared. Poor performance at very low BER. So, BER cannot be below a threshold, otherwise we will keep iterating and not converge. Because turbo codes operated at very low SNR, channel estimation tracking is critical to the decoding process, because the efficiency of this turbo codes is at low SNRs only. So, yes, that is kind of a disadvantage. So, now let us summarize what we have done today. We started off with a brief introduction to turbo codes. We looked at what is the structure of turbo codes, how concatenated convolution encoders can be converted into turbo codes. We looked at the encoding process, and finally, we looked at two decoders and then looked at the importance of interleavers for turbo decoders. Finally, we looked at some examples to show the efficacy of these turbo encoders and decoders. With that, we come to the end of this lecture.